Hi everyone, welcome. This is the first of our Affinity Hire Speaker Series. I'd like to remind all of you that you're welcome to get food at any time. We do have a sign up at the door, so please make sure you sign up if you haven't already. The Speaker Series is hosted by the Office of University Diversity. Dr. Diane Ruff-Woods is here supporting, and also the Office of Sustainability. And I do want to also thank our Provost and Academic Affairs for supporting the Affinity Hires and events like these as well. So we're doing this for a couple of reasons. One, we want to highlight our faculty that are doing really great work, but also the themes of sustainability and diversity and how they're connected. And we have these Affinity Hires because the work they do joins those two topics together. We're hosting this so that people understand the connections, but also the importance of this work. So thank you all for being here and being open to this conversation. Our professor today is Dr. Ryan Smith, who's going to be speaking with us about leading global transformation to a sustainable energy future. I do want to mention, too, that we do have 4 Affinity Hires this year in anthropology and psychology, sociology, and physics.
Philosophy.
Oh, it's philosophy, not psychology. Thank you. And then we'll have 4 more next year. Is that correct, Ryan? And these specialists really grow together and work together as a cohort. They're co-conductors of concurrent research, and they support each other professionally. So it's really a unique thing to see at a college campus, these people working together. It's exciting, it's a great thing, and we thank all of you for being here. So with that, I will pass it over to Ryan, and
Thank you.
There you go.
Thank you all for being here. So I wanted to open with an image of our campus, right? You might be looking at it and you're like, I don't know that campus. Is that my campus? Does anybody notice anything strange about this campus versus the campus that you see every day?
Hamilton Hall.
So you might notice this building's not there, right? Does anybody know the date that it was imploded? Somewhere around 2012, 2011?
2 years.
2 years ago. Okay. So one of the things I wanted to highlight, though, hi, welcome, is that even when this building was here, there's already solar panels on 2 of the buildings, right? And now we have even more. And so I wanted to talk with you not just about solar energy. That is one of the things that I want to discuss with you. But I also just want to talk about how you can take a leadership role and how also our campus is engaged in this greater conversation around sustainability. And specifically, the topic I want to talk to you about today is about energy sustainability. And how can we keep moving things forward in a way that future generations can continue enjoying? So when you think about sustainability, right, what do you think about? You might think about the electric car parking that's happening right out in some of the parking lots there. You can plug in your car and you can charge it for free, right? Seems like a pretty good deal, right? And you think about maybe some solar panels on roofs. You think about people walking to work or running, and green forests and open spaces, things like this, right? So maybe those are some of the things that you think about. And you might sort of start to clump them all together in sort of one way of thinking about the world. But I want to stretch that picture a little bit today, that actually sustainability is not just about the environment. It's also an economic and a social issue as well. So you can see this kind of diagram here that talks about sustainable development basically as where kind of all those 3 concepts are actually coming together. So I'll give you my side on things, and then hopefully you can start to put the puzzle pieces together for how social justice and economic prosperity actually fit into this picture. So in order for sustainability to happen, in other words, our actions to lead to future generations being able to continue on with a pattern that actually allows people to live and actually coexist with their natural environment, it requires quite a bit of collaboration and cooperation, both within a campus, within different departments, right? Different perspectives, right? So we have to have that diversity piece that actually is really an integral part of actually making that cooperation to happen. And then branching out further, once we've got that part, is actually between people from different cultures, different countries, working together, coming up with agreements and plans together of how we can actually step forward in a sustainable fashion. So I want to start off thinking about energy supply. So this is one of the things that really got me interested in studying renewable energy. So my research in the physics department has a lot to do with studying solar energy. So different ways to take energy from the sun and turn it into useful forms of electricity that we use, useful forms of energy such as electricity, such as heating things up, things like this. And so if you want to look at like a big picture timeline, human history, if you want to look way back, 2000 BC or even more, And you want to think about, how did we meet our energy needs, right? So these are all the things that you enjoy these days, right? So like, being able to wash your clothes or have yourself moved around, right? If you think about it, for the first however many thousands of years, people basically met their energy needs through slavery, using animals to pull your things around, right? And to do work, plow your fields, and burning firewood, right? That's pretty much it. Think if there's something else that I missed here, but that's pretty much how people met their energy needs besides doing something themselves, right? And then something really special happened. We discovered fossil fuels. Does everybody know what that is? What it means, fossil fuels? Anybody just want me to say what that actually means? So this is kind of an interesting phenomenon because something really changed actually, like socially as well, right? And economically, everything was kind of was radically shifted at this point, right? So you're looking at pretty recent, right? So here's 2000, right? And you're looking 10,000 years back since the end of the last ice age. And now something really special is happening. So we're benefiting from fossil fuels. So we have coal, natural gas, and oil, and we're burning all these things, right? That are these hydrocarbon compounds, and it's allowing our lives to become quite a bit more rich than they were, let's say, 1,000 years ago. However, if you look at the story, you might guess that there's an inevitable end to this, and we're actually living in a really special time in human history, actually in the planet's history. We're actually like the only people. Now, you might not think of it like as so special because you're like, well, my parents and their parents and their parents and their parents also benefited from fossil fuels, and maybe my children and their children and their children will also sort of benefit from this thing. But if you think about it, that's not really that much compared with how many generations of humans have lived on this planet, right? It's very, very small, very special time in human history. But the inevitable is that these fossil fuel resources will be gone. They'll be totally gone, right? They're something that have accumulated for a long, long time, and we're now reaping the benefits of that. So if we want to continue after these things are gone, we either need to turn to nuclear energy, right? So fission or fusion processes. Fusion is not something that has yet become a reality for a kind of sustainable energy, but actually shows potential promise. It's the same thing that the sun uses actually to create energy. Or we could look for geothermal energy, which is a possibility, but it's a little bit low for what we're demanding at this point, and solar energy. Or we can go back. Boo. So just letting you know, that's the stakes here, okay? That's what we're looking at. And so I want to talk with you about solar energy, right? And how we can actually use this, okay? And to be fair, these fossil fuels are also a form of solar energy, right? They're things that were once living, they're carbon-based life forms. We're carbon-based life forms. Plants are carbon-based life forms, right? These are things that were once living, but it's accumulated over millions of years, and we're taking all that solar energy and enjoying it right now, okay? So very special time in human history. And so I just want to talk about how we use energy here. So this is kind of like a little picture here of you and how you use energy, right? So you think about all the things that you did. So you must have gotten here somehow, right? So how did you get here? Well, did you walk? Well, even if you walked, you actually used energy. You had to eat food, right, to actually come here, right? So you're refueling right now, right? So, and you might have driven a car, taken a bus, right? All of those things take some kind of energy. So if you kind of added it up over the course of the day, you might wonder, well, how much is that compared to, like, let's say if there's energy in food and there's energy in the electrical sockets and the gasoline that I have. I know you can't eat gasoline, but they both have energy. If you could compare them to each other, like, how would they compare? So I'll propose for you a little bit of math here, that a watt hour, right? Remember, you pay for kilowatt hours. In California, it's about 25 cents a kilowatt hour. That's about 1 calorie, right? So if you think about it, if you ate 2,400 calories per day and you did the conversion, that's about 100 watts. So I mean, just think of that as that you have the potential for just you, if you're just you're the only one, eating your Cheerios and then riding on a stationary bicycle that's connected up to a light bulb. If you're riding this thing, this thing, you can keep a light bulb on, 100-watt light bulb, right, incandescent bulb, 24 hours a day, right? That's kind of like what you can do, okay? So if you imagine thinking about the amount of electricity that you have to pay to keep one light bulb on, it's not that much, right? So how much do we actually use energy-wise? Well, it turns out the United States, you use 10 kilowatts, right? Which is the equivalent of, you take 100, you multiply it by 100, you get 10,000. So it's the equivalent of having 100 light bulbs on all the time. And these are not the energy efficient ones. These are like the regular light bulbs, that, the incandescent bulbs. So 100 light bulbs, 24 hours a day, 365 days a year. This is kind of your equivalent, right? If you want to think about one person as being 100 watts worth of effort, right? So I guess I want to maybe just give you a kind of discussion topic that maybe you might check in with your friend or somebody you came with to talk today. So institutionalized slavery in America ended in the 1800s. I don't want to get into a deeper debate about whether or not slavery still exists. It does. But in the institutionalized sense, you think about people were being used to meet all of the different energy needs. And I wonder, do you think that it was a coincidence or some great humanitarian gesture that there was a switch right around the same time that fossil fuels started to become mainstream? So that's something I want for you to think about and just challenge you to engage in that kind of conversation. It's a little scary, right, to think about these kinds of things, but I think it's important to think about how we've progressed as a society. So I just want to highlight the fact that fossil fuel demand, if you look at the different types of fossil fuels, so coal, petroleum, natural gas, and you add up all those things, you get this black line here that talks about the metric tons of carbon per year that we're burning worldwide, right? So we're talking 8 billion metric tons, right? I can't even imagine like how many shipping containers that would actually take to do something like that, right? But that's a huge, huge amount. And if you think about it, so the burning of carbon, right? You take a C and you have to use oxygen from the air. So you have a C and an O2, right? In a very simple chemistry equation, that makes CO2, right? And I think everybody sort of intuitively has heard of, okay, yeah, CO2, carbon dioxide, right? So carbon and two oxygens. And that's a greenhouse gas, right? And so there's another issue here is that it's actually also contributing to the warming, the average temperature warming of the Earth. So it's something that we're increasing significantly the amount of carbon that we're burning, and we're also producing quite a bit more carbon dioxide. So I think everybody knows by now that there's a great concern about the burning of these fossil fuels as actually having a non-trivial contribution to the average temperature of the Earth increasing. And so scientists use models to try and understand what has happened and what is happening, and try to make a prediction based on that information, what will happen. And so a model, you can think of it as kind of our working idea about how the world works. And so this idea is shown as the pink line, or the pink sort of band here. And the thickness of that band shows you how much uncertainty there is in this kind of model. So if you think about it, this blue line here is a model that only includes natural forces. So for example, also includes volcanoes and includes sunspots and includes different things that are sort of happening independent of us. It's kind of hard to extricate us completely from our natural habitat. But if you then include the effects, mainly the effect of that carbon that I showed you in the previous slide, and you look at how the temperature of the Earth, this is the average temperature around the whole Earth here. You can see it's a little bit on the cold side, 57 degrees, right? But this is average. Then you can see that it actually tracks the measured increases in temperature pretty well. I mean, of course, there are some disagreements, so maybe we don't understand everything, but I would say that that's we have a pretty solid grip on what's happening. Furthermore, there's a really great project called Berkeley Earth, led by Rich Mueller, that actually compiled all the data because there was some concern about the integrity of data, and really checked it extraordinarily carefully and narrowed down the error bars on this significantly, and was able to basically get the error bars are very small. So you can see that the thickness of this band here becomes smaller and smaller and smaller as we get to more recent dates. So we're getting very clear now on what is happening, and we're also getting clear on acknowledging a cause and effect. And it's so great that now, if in surveys, over 99% of scientists have agreed that humans have a non-trivial role in the increase in the average temperature of the Earth. So this is a really important situation here. I'll give you just a quick bit on the science here of how this is working in case you haven't seen this before. If you've seen Al Gore's Inconvenient Truth, this may be old hat to you. But the sun actually warms our Earth. I think that this is a good thing, actually. If it didn't, then we wouldn't be here. And there's actually, our atmosphere contains CO2 among other gases that actually will trap in the heat. So the light comes in as mostly visible light, some infrared, and then when things become warmer, they actually emit out infrared light. You can't actually see that with your own eyes, but it's emitting infrared light. And it turns out that by interacting with CO2 and other gases, a part of that is reflected back down. So this is called the greenhouse effect. It's not exactly the same thing as what happens in a greenhouse, but it's a close approximation to kind of understand the effect. If you want to get deeper into the physics, I'd be happy to talk with you. But the idea is that actually, from a physics point of view, if you did not have that atmosphere and you just had the sun going on it, we would be at about minus 100 degrees Celsius. We'd be really, really cold. Something like this. I don't remember the exact number, but it'd be far too cold for life as we know it to exist on this planet. But it's actually because of this atmosphere that life can exist. So actually the greenhouse effect is not such a bad thing, actually, right? But what is a challenging thing is the fact that too much of the CO2 bringing things out of balance can cause a warming that will set all life as we know it out of balance. And we depend on this, right? We're not living in a bubble here. We actually depend on other creatures and plants and millions of years of evolution of this kind of balance to happen for us to survive, right? So. To kind of underscore this situation, so here's a picture of a glacier in Alaska at Muir Glacier, and it was taken in mid-August 1941. Okay, here's that same glacier, 2004. Okay, now I'm not trying to make the claim here that we did this to this glacier, right? That's not really exactly my point. And to look at something like Hurricane Katrina and say, oh, we caused that, to attribute any single event to the human behavior, I don't think is quite appropriate. But we do know that one of the things that models predict is that the average increase in temperature will lead to melting of glaciers like this, and will lead to the increased sea level, right, which will put civilizations which are at lower elevations compared to the ocean underwater, including Florida. And we will have also an increase on average, so statistically, in severe weather patterns such as Katrina. So it's something that's worth paying attention to, that we're involved now in this process. And the full damage may not be known for a whole century, right? So if you look at this, this has anything to do with global warming or climate change. This is actually a picture of cigarette consumption in the United States. And so if you look at this here, well, he's talking about cigarette consumption, right? So if you look at it, we passed laws back in the 1960s to say, hey, actually, cigarette companies, you have to tell everybody how bad this stuff is. And smoking causes cancer, right? It's no surprise to anybody to hear this at this point, right? But it was back in the 1940s when you'd see your favorite movie stars, having cigarettes, and they thought, okay, it's not such a big deal, right? So some policy went into effect, and look at that. 25 years later, you can actually see really visibly like this hump going down, and a little bit later for women populations, that cancer rates, lung cancer rates specifically, are dropping down, right? So seeing those correlations, there's like a time delay, right, between these things. So I just want to highlight that idea for you as you're thinking through this problem, that the problem may be actually far worse than you even imagine that it is. It's that there can be a delay of this effect. So we're in a crisis, okay? And this is a Chinese character, and please correct me if I'm wrong on this, but I've read that the Chinese character for crisis is actually a combination of danger and opportunity. So if you think about it, I guess I don't want to be Debbie Downer and say, hey, like this is it, this is the end, folks, let's jump ship, right? But like, actually what I'm trying to say is that it is really important that we pay attention to how much danger we're creating, right? So the big picture is that we may make the planet unlivable for humans, right? So, yes?
Also, it means urgent.
Urgent. Okay.
First one means danger and urgent.
And danger and urgent. Okay. Oh, interesting. Okay. So, all right. So it is urgent. Yeah. Okay. So danger and urgent. So the urgency that I see is that we as humans don't always play well together, right? So we're still working on how to socialize and how to talk to each other, how to actually cooperate, right? And so if this is opportunity, I have it still in my brain like that, so I'll have to think through that a little bit more deeply. If this is an opportunity, the opportunity is to actually foster a greater collaboration and connection as we move forward together as a human society. So if you look at what the sun can offer us, all of the energy that we use could be satisfied by putting solar panels at, I just picked some random non-controversial place here on the planet just to show you the relative size, is South Africa or Mozambique. If you put this amount of area, now I realize it would be totally impractical to put like a field that big and then try to send out cables to everybody, right? But think about that amount of area covering the Earth with 10% efficient panels, right? It's not really that much that we're asking for here, right? We already have 15%, 20% on average is what you typically see in an installation like the ones I'll show you some images of that we have on campus. But if you had just that much, converting 10% of sunlight into electricity, you would satisfy global power demand, right? So it's just kind of like, another big picture thing to imagine that that's actually possible. So 173,000 terawatts is available, some huge number that I can't even imagine how big it is, right? And here we are, humans using 15 terawatts, right? That's the whole planet, everybody included, right? So even if we doubled up or multiplied it by 10, we could still definitely satisfy those needs, right? If we figured out a creative way to actually do this. So this crisis, right, could potentially lead to further innovation and trying to figure out how could we actually harness this amazingly abundant and renewable resource, right? Instead of using the ones that are the most convenient that may actually be creating more problems than we had realized. So, yes?
Go back to slide when you meant plants.
When I say plants, I mean growing plants and then using them to, say, make some biofuel or burning them to use the heat from that. Yeah. And in a sense, okay, so I will just say then that in a sense, that is a kind of solar energy, right? Wind is also a kind of solar energy. If you want to look at it more from a physics perspective, you've got one part of land being heated up and another part that's colder, right? And so that difference in temperature will create a pressure difference, and that pressure difference will create some wind, right? And you can use the wind, right? Same thing actually with hydroelectric, right? So how does the water get up there on top of the mountain in the first place? Well, it's the sun, right? Sun actually is giving the energy to those molecules, right? It's a lot of the molecules, and they go up top of the mountain, and then they go back down, and that's the recover of that gravitational potential energy. So for those of you who are in one of my elementary physics class, we can talk more about that. And you can also see that there's smaller possibilities to use tides, for example, right? So that's actually energy from the moon. Okay, it's not so much compared with the sun, but it may be in certain areas, especially with one that has ocean tides moving back and forth. Maybe that does seem like a sustainable thing to do. Or if you're in a place that has high geothermal activity under the ground, you can always use differences in temperature to create electricity. So there's lots of creative ways, right? So it's not going to just be one sort of silver bullet, but actually a combination of efforts and innovation to meet our energy needs without using this non-renewable source of energy. So I just want to highlight a few successes, right? Since I gave you this like horrible picture of our planet is doomed and everything's done, that we're actually making some progress, and both on a national, international scale. There's the Paris climate talks, right? So everybody knows about that, right? So they call it the COP, the something of parties, oh my gosh, it's okay. And so So our nations have met together, right, to try and deal with this problem for a number of years now, and have either failed to reach consensus, or when we did reach consensus back in Kyoto, that it actually wasn't then ratified by our Senate. And so there's kind of this like a little bit reluctance, let's say, especially with the big players, right? Who are the big players? U.S., China, India, right? So those are some of the biggest fossil fuel burning countries, right? And so those are maybe in some ways some of the most important countries to sort of get on board first and set a role model for maybe how the rest of the world should start to do things, right? It doesn't make a lot of sense for a country like the U.S. to say, walk into another country and say, hey, you know, y'all are doing it wrong, and they're like, well, wait, how did you get your start, right? So there's a bit of a, you know, there's some kind of how do you say, ethics in how this march needs to be set forth. We have a greater responsibility, and so good news is that the Paris Climate Agreement was a success, and it was actually that 195 nations agreed to limit global warming, right? So. You know, that seems a bit naive, and there's not say you can't just sort of do that. You can't just say, okay, now we're gonna everybody turn on your refrigerators, right? We're gonna cool it back down. But there's an understanding in there in that metric that it's because of our behavior, it's because of the burning of carbon-based fuels that's leading to an increase in the greenhouse gases that's causing the increase in temperature. So it's kind of like there's the cause and then there's the effect. So the effect is what they're sort of aiming for. The cause is that they're actually making a commitment to increase the amount of renewable energies and find ways to more cleanly burn coal. So coal, by the way, is the cheapest fossil fuel to burn, and it's also the dirtiest. So then also the U.S. Passed the Clean Power Plan in just this December, so just a little over a month ago. That was the largest step that the U.S. has ever taken to cut climate pollution. So that's a really interesting response. It's a kind of an interesting first move, let's say, in response to the Paris climate talks. And so not only does it set federal limits on carbon pollution from existing power plants, so it's doing a retrofit and also a new standard for new coal plants, but it also gives incentives for wide-scale renewable energies nationwide. So it's innovative. It's something that's a new policy that I think is going to actually lead to even more generation of clean and renewable energy. California, by the way, is the leader of all the 50 states in doing progressive things. You might notice that we have quite a lot of wind turbines down in the southern part of California, and Jerry Brown passed the so-called SB 350 Senate bill for Clean Energy and Pollution Reduction Act, and the goal was 33% by 2020, which we're on track for. But now the goal is 50% of California's energy needs by 2030 are met by renewables. Wow, it's an ambitious plan, but it looks like that's actually a realistic thing at this point. And so if California can show that, right, and can really demonstrate that, it may be, and also keep their heads above water, right, financially, then maybe it's a good role model for other states and then finally other nations to think, well, you know what, actually this seems like a reasonable kind of thing to do. And then the last thing I just wanted to mention was that just a week and a half ago, Congress extended these production tax credit and investment tax credit, both of which boost renewable energies, wind and solar, for residents and businesses that want to start installing. So it basically gives an incentive, economic incentive, for installing these things. So we have a lot going on. And on our campus, we're also leading in sustainability and trying to do our part in tackling climate change. So I just give a few highlights of some of these things. I know I tried to play around with a font forever, but I couldn't find one that read. So in 2014, that was the first time that the campus hired a sustainability director. And so there's now a paid student internship program dedicated to sustainability. So for those of you students that are excited and passionate about this issue, we have a sustainability club on campus. We have possibility that you could actually do work for around sustainability issues and also get paid for that. So it's a really exciting way to get involved on our campus. We've recently had the first time, this should say 2015, I believe, the first time that the Campus Sustainability Committee meets, we had an official greenhouse gas inventory, right? So we can assess where we're at. And in 2015, at the beginning of 2015, our president signed the university president's carbon commitment, which is basically to set up an infrastructure to try and boost renewable energies and minimize our impact of producing carbon dioxide. And so some other things here is that our Dining Commons has committed to zero waste, and there's right now a food audit happening. And so there's a Weigh the Waste campaign happening to try and assess where we're at, how much food is being wasted, and we're trying to think of creative ways to minimize the amount of waste. There's a new recycling program. You're going to see these 3 bins coming in this spring, hopefully by the spring, that will actually be a little bit more, say, present on our radar as we're moving about campus, thinking about recycling, thinking about minimizing the amount of waste that we're producing. Also, there's a lot of work happening to produce more sustainable transportation options for commuters. So this is a commuter campus in many ways, and a lot of people are coming from around the East Bay. So there's also a lot of work happening to make this to happen more sustainably. Yes. New recycling bins, I'd be happy to talk with you more about it afterwards. We can also check in with our sustainability director. So, also, so I'm part of, as Jillian Buckholz mentioned, I'm part of one of the 4 Affinity hires on sustainability and diversity, and there will be 4 more coming in the next academic year. So there's a lot of effort happening, plus my research and other professors' research around campus, including Dr. Eric Helgren, are working on issues related to sustainability. In other words, solar energy production, also LEED certified building structures. We have quite a lot of interest on the teaching and on the research front, really trying to help people get more engaged, help students get more engaged, and use this place as a training ground for actually learning how do we commit to making a more sustainable world. So you can see here some nice images. This is on top of the SF building, the new building on campus. This is one of the side, and then up here on the roof are these panels here. And the numbers are, I forgot, it's 160 kilowatts on the top here, and somewhere around 80 kilowatts on this bottom part here. But the number to remember is that campus-wide, we have about 1 megawatt of solar power that's being produced. And if you think about that, actually, how does this scale? Well, in 1 square meter, right, on the Earth, there falls about 1 kilowatt of sunlight, right? And this is at high noon, right? But and if you think about that, if you scale it up, right? So some people say, solar will never work because you just need so much space. Think about this. 1 square kilometer is just multiply 1 meter by 1,000, you'll get a kilometer, right? So you have to multiply by 1,000 and then by 1,000, right, to get this bigger square. Now we're talking from a kilowatt up to a gigawatt of sunlight, right? So it actually that's about the same as a coal power plant produces, right? So granted, that would be with 100% conversion efficiency, right? But it's not so far off target to imagine that even a campus like this could meet all of their energy needs, right, based on solar energy alone. So I also just want to have one slide here just to show you. This is not a research talk, but I just wanted to share with you some of the research that actually is happening on campus. So my research, part of it involves looking at quantum dots and how you can insert these into materials to improve solar cells, right? So you have these solar cells, these panels that are going up on the roof, and you have sunlight going on them, and then somehow there's these cords connected to them, and you're actually producing electricity, right? And so they do this pretty well. Most of them are made out of silicon, right? The same thing that's in your computer or in your smartphone. But we're looking always for better ways to produce solar energy, solar electricity specifically. And so one of those ways is actually by inserting a dot. That means a small cluster of atoms into a matrix of a larger crystal. And it turns out that by doing this, you can actually tune the properties of a material. So we put in a bunch of these so-called dots, and here's actually a picture of this with a 100 nanometer scale taken from a scanning electron microscope that shows you all these little clusters of dots of different kinds of atoms embedded into another matrix. And we're looking at these nanometer scale size things because it turns out that as you tune the size of these dots, so here's like 3.7 nanometers down to 2.3 nanometers, you notice something interesting is that you're actually tuning the colors that these crystals can respond to. Okay, and so you can actually see this very visually here, that different size quantum dots actually glow different colors when illuminated with UV light. So that's kind of interesting. So the silicon solar panels are really good at taking one part of the sun spectrum and converting that into electricity. And so what we're looking at doing is trying to find different mixtures or combinations of these so-called dots, these clusters of atoms, and try to find ways to actually use most of the sun spectrum. Now, of course, there's always a catch. One of the problems is that charges tend to stay aggregated at these and stay trapped on these little dots as if they were islands, right? So we're looking always for more creative ways to try and get these electrons that we create from photons from the sun to actually have them go out and create a current and say charge a battery or charge your cell phone, whatever it would be. So we're looking at that, and those are some of the research that's actually happening here at Cal State East Bay. So just want to then say, in summary here, basic research is spurring innovations, and that's also something that's driving the costs down of solar, right? So there's a lot of factors in all this. And then I just want to say here that the demand for solar energy has skyrocketed, right? And especially, I mean, if you look in the last decade here, we're looking at there's huge amount of production, and another really important part when we talk about collaboration and economic development is that as there's more demand for something, right? Even if it's a subsidized thing, right, from our government saying, hey, put in these solar panels, that's actually getting the ball rolling, because what's happening is that more people are producing this. You get an economy of scale, you get more collaborations and ventures happening, and the cost also scales down. So you think about 40 years ago, we're talking about $76, and it's the amount of money that you'd pay per installed watt. Now you're talking at 36 cents, right? So we've been able to push this cost down to a level where it's becoming sustainable, right? It's becoming actually cost effective to this sense that somebody who might be living in a rural area, right, in a poor country, might actually think, okay, well, that's actually a reasonable way then to say charge up some of the things that I use, right, or keep the lights on, right? And so actually Karina Garbisi and Eric Halgren started a course last year. It was really exciting, called a solar suitcase class that invited students from many different majors to come together and actually work on how do you actually convert this solar energy into things that are useful. Went in and educated middle school students and actually sent out these suitcases that do the conversion to specific areas in the developing world. So it's an exciting thing that we have happening here, and we're definitely seeing all kinds of different ways to engage. A lot of times people ask me, so hey, what's the cost of a solar panel, right? And it's kind of like, it's hard to say exactly what that number is. You say, well, I don't know. I mean, you could talk about cost per watt, and then they're like, well, what does that actually mean for me? Well, if you go to the Google Sunroof project, actually everybody in the Bay Area's house is kind of on there. You just type in your address, and it'll actually tell you what would it cost for you to put solar panels up on your roof. And so kind of one nice metric is to just look, how many years would it take for me to pay back? So then I'm basically at a kind of a 0 point, I would have been paying just as much to pay my electricity bill, at that 8-year point. That's kind of where it is, and that number continues to go down. So kind of just to give you some metric. And so I just want to end with, so there's a saying that I've heard that we don't inherit the earth from our ancestors, we borrow it from our children. So I try to live with that mindset and try to think about, how it's just that I'm borrowing here while I'm just, walking around here on planet Earth. And so I hope that you feel some excitement and a sense of urgency as we're approaching how we can each play a meaningful role in the crisis that we're in. I'd like to also just to give a special thank you to Diane Rush Woods and Carl and Chris for the organization of the Affinity Hire Group, and Jillian Buckholz for her continued support and conversations around sustainability, to Karina and Eric for all your inspiration around the Solar Suitcase Project and renewable energies in general, to Evelyn and Laurelyn over at facilities working on the energy management, to the other members of my Affinity Hire Group. I don't see any of you here today, but that's okay. And then the physics department in the College of Science. And I'd like to thank you for your attention. you have any questions? Yes.
I'm wondering, like, fusion. I saw an article in Science News where there's a lot more startup companies actually investing in fusion and thinking that it's a possibility. I'm just wondering what your perspective on it is.
So when I was an undergraduate, I did a research for undergraduates experience over at MIT at their Plasma Fusion Center. And it worked at this thing called a tokamak, which is basically a giant magnet about half the size of this room that is made to suspend a channel of plasma and the idea is to create fusion, right? That is to say, slamming light atoms into each other. For example, a hydrogen and a hydrogen to make a helium atom. And it turns out that the sum of the parts is actually a little bit less in this case, right, than the two individual particles before the fusion happens. So that extra mass that seems to be missing, right, that's where this E equals mc squared comes in, right, so that mass can be converted into pure energy, right, and so that energy is basically heat. And then once you've got the heat, then it's like, whew, we know what to do with that, right? So coal plants and nuclear fission plants all take advantage of that. They use heat to make steam, and the steam makes some turbine spin around and makes electricity, right? So we can go over the details of that. But you're trying to just make heat, basically, make a lot of heat, right? And the issue has been that it's very difficult to mimic what's already happening in the sun. And we've been trying, and we've been thinking about all kinds of different strategies for this. But this has been an ongoing research effort since about the mid-1950s or so. And so there's a little bit of a joke in the field that nuclear fusion is just 50 years out and always will be, right? And so I don't think so. And I think that at some point we will have breakthroughs. And I think it's worth continuing to watch this and see if we can actually get sort of a net positive, right, where the energy that we put in is less than the energy that we get out. But so far, only in very limited circumstances are we actually at that situation. So on a larger scale, it has not been accomplished. But also look at ITER at the Lawrence Livermore National Lab. There's active research happening in that area, thinking about ways to use intense laser pulses to create fusion events. So there's active research happening there, trying to figure it out. In the meanwhile, I suggest that we search all solutions. But I think that who knows? It could be something viable. Yeah. Yes.
Ryan, I've got a couple of questions for you. One, I don't know if you saw the debate last night, but Hillary Clinton said, I think in her finishing speech, that she wants 500 million extra solar panels that would provide enough energy for all of America. So has she got her math right? 500 million solar panels?
So half a billion, and let's just say that each panel is 100 watts, right? So there's a third of a billion people here in the United States. So, that would mean 3 solar panels per person, and that would mean 300 watts equivalent per each person. But remember, each person's using 10 kilowatts, right? So that's about 3%, if I got my math right? 3%. So it's something, it's not nothing. But I don't know, maybe she meant bigger solar panels, right? So I mean, it's really hard. I mean, you know that there's like a smoke and mirrors game in any kind of business, right? And so when people say things, ask them lots of questions. Be like, well, what do you mean 100 watts? Like, well, what do you mean at full daylight, or do you mean peak, or do you mean average? Because I mean, you do know that the sun is like, or not the sun, it's on the other side, but the Earth is rotating around, so it doesn't see sun for half the day, right? So are people, it depends on who you're talking to. Is the person who's trying to sell it to you, or the person who's trying to, get the insurance? Are they going to use the fact that there's the, not the sun half the day? We need to agree on a metric when we talk about this stuff, because you just say some number like, oh, billion solar panels, like, oh my gosh, that sounds like a lot, right? But on the other hand, like 3%, if you said, I want to increase by 3%, they're like, yeah, okay, it seems reasonable. I mean, look at California, they're doing it by 50%, right? So it's not maybe so miraculous, let's say, yeah.
Yeah, my second question, I'm working with the folks down at Moss Landing Marine Lab to develop an aquaculture program.
Oh, great.
So
my colleague Alex
Parker's
Parker's there.
Really interested in is the future of algal biofuels, and the idea that if we grow algae, particularly using wastewater from cities or from farming, we have a triple. We get a fuel that's using sunlight, we take nitrogen that's going out into our ocean and back into our atmosphere, and we start clawing back some of that carbon to create a fuel cycle that is actually taking back some of the carbon that we put back in, as opposed to using carbon that's already part of that, the biology that's already growing under ambient conditions. So
Right.
what do you hear in the physics world about the future of algae and how they might be a solution to global warming?
Well, I think it's a great idea, and I'm not a biologist, but I do know that creating life and manipulating it needs to be done with care. And so I feel a little bit concerned or hesitance to get on board with such a plan without knowing how life continues to mutate and adapt to circumstance. The dream sounds amazing, and I have a friend who at the NREL, at National Renewable Energy Lab in Colorado, working on similar type of idea. And it seems that this could be a great way to harness solar energy. So especially because of the fact that if you could put it in oceans, then you're not really limited by land space, right? So if you could find some kind of creative way to sort of make use of that, I don't know how that would look, or how you would contain it, right? So that it didn't just sort of spread over to places where it might be accidentally causing problems that you didn't intend, right? But at the same time, it is a form of solar energy, and to my knowledge, plants can usually take that 1 kilowatt per square meter and convert about 2 to 5% maximum of that energy, right? So if land is no issue, right, because it's maybe an ocean, well, then that seems like a great idea, right? Because you're taking advantage of a resource that's essentially is abundantly available. So, yes.
Two questions. One is, in the past, and I think when people talk about the environmental sustainability, they talk about the pollution.
Right.
In the past, like 15, 20 years, and people start to talk about the global warming.
Right.
And I just wonder whether is it the science behind that, or is it just pure politics? Because to me, I just came back from China.
Right.
And when
Right.
I talk about pollution, you can really see it.
Absolutely.
But global warming is still far away.
Yeah. So it seemed totally. I totally know what you've been. I've been to Beijing not too long ago, and the PM 2.5. I'm sure you all maybe have heard of this. PM, this is the particle size, 2.5 micrometers. And so it's this sort of in-between size that's very difficult to filter out and gets into a respiratory system, and you can visibly see it actually, right? In a lot of cities with high pollution, and they're making a lot of strides to say, well, why don't we use like electric bicycles, right? And why don't we try to find ways to say burn the fossil fuels more outside of the cities so that we can leave the cities cleaner, right? And that's a much more visceral thing, right? If you see it every day and you're not out here in sunny California where you're out, most days sort of being able to look out to the Bay and to San Francisco, you maybe don't think of that as much, but that is definitely an issue, and that's compromising people's ability to live, a long and healthy life. So that, to somebody who's living there, may seem like a far more urgent issue. And so I guess what I'm talking about is something that's even bigger picture than that. I think that we will handle these things, and I think policy will have a lot to do with it. And if you, as an example, if you take a look at the Montreal Protocol, so there was a hole in the ozone layer kind of around Australia area, and then after the passing of this back, I guess it was in the late 80s, early 90s, that there was just like my tobacco thing that I showed, there was a kind of a healing in this, if you want to think of it like that, that there was a repair that happened almost on like a 5 to 10 year time scale. So pollution, I think that's something that is doable. Like that's a very doable thing. This is something where we've created an entire global lifestyle, right? Our trade, our flying on airplanes, everything about my life has sort of centered around the production and consumption of fossil fuels. And so it's going to take a little bit of effort, let's say for a lot of effort, right, to create a new sort of infrastructure that visualizes energy consumption and production in a different way. Which is not to say that we need to like stop consuming 10 kilowatts. Actually, that's about the standard of living that it seems like most developed countries are sort of landing at, something along that, maybe 5 to 10 kilowatts. So if that's the goal, well, let's find ways to do that in a way that does not hinder either the day-to-day every life or the long-term future.
So second question is the solar energy or other alternative energy really clean?
Is it really clean?
Yeah, because we know it's cleaner in terms of the emission.
That's right.
But what about the materials generate the power and everything? Because a lot of people say that it can be very toxic long term, and that you can't really get rid of that. Stay with you all the time. So
That's
what is the
it's
science
a
behind that?
yeah, absolutely. So it's a great question. I mean, so silicon, right? I mean, just comes from sand, right? Silicon dioxide, right? And you take the oxygens away somehow, right? Actually, it's a very chemically intensive process that involves a lot of energy. But if you can rip apart the oxygens, you've got pure silicon. You can work with that and make a solar cell, right? And then, of course, you've got to have some metals around this, right? And you've got to have manufacturing process. You have to have infrastructure around that, right? None of that stuff is free. But if you could get that to the point where a solar panel then lasts for 100 years or 200 years, like a just wild dream, then you might think, well, it's not really such a big deal, right? It's less bad, let's say, right? But another aspect of my research is actually looking at a new material called graphene, which is a single layer of carbon atoms. And I didn't include that in here, but graphene is thought to be really interesting because it's pure carbon. If you could really make, this is, again, like out pie in the sky kind of dreaming here, but if you could make a solar cell out of a single layer of atoms that are carbon, which are not toxic, and you could harness solar energy from that somehow, right? Then when your solar panel, stopped working for whatever reason, you could throw it into your compost pile, right? So that's maybe kind of a far out dream for maybe some of the innovations of science and what could happen, right? So that's also, it's not just to improve the cost, but it's also to it's to improve the cost, to make it more sustainable, right, from a sort of chemical and energy intensive point of view as well. And it may be that by exploring these various materials and different kinds of nanoparticles, we might arrive at a solution finally that's like, oh, this is a very sort of safe, it's abundant, it's easy to produce. One of the dreams also I have is, there's a type of semiconductor that shows up in a kind of a liquid format called CIGS. And copper, indium, gallium, selenide, right? So some of those don't sound like such great metals, right? But the idea is, well, what if you could replace some of those, for example, with aluminum and zinc? Could you form stable chemical bonds, put them in a liquid ink cartridge, send them to people around the world, and they just put it into a printer and they print their own solar cells, right? So, and maybe if that material, everything that they used was safe, right? And was something that if somebody, if it got lost or if it got into the water supply, no big deal, right? So that's kind of one of the goals, the longer overarching goals in producing a safe, clean energy supply. Yeah.
Well, actually, now I want to follow up on that because until you get this nice, clean, graphene, whatever, a solar cell is basically a big integrated circuit. And if you look into the manufacture of integrated circuits, there are a lot of noxious chemicals.
That's right.
And nobody wants to talk about that. So, I mean, what do you do with them?
What do you do with that? Right.
And so is it really worth it?
Right. So I think that, to also kind of reiterate within what I was saying is that you look for methods that are scalable in a sustainable way, right? So the idea is not just to do whatever it takes to make, to be able to harness solar energy, right? Whatever it takes, right? Actually, like, we can go about this in a more systematic and organized fashion, right? So what we're seeing is sort of if you want to think of it as the first step of consciousness, where we're looking at it and saying, oh, there's renewable resource, we should try to use it. And we're like, okay, let's just find some way to use it, right? And so we're going about it in a kind of a messy and fast and loose kind of way. So what I'm proposing is that why don't we put more effort into really thinking about the different ways that we could do that, and then come up with a more organized approach, with our global community in terms of how could you, say, deal with some of these problems? Is there another type of chemical that you could use that's not quite so toxic, or that maybe even isn't toxic?
Yes, that's
right.
great, but at the moment they're putting up silicon-based solar cells.
I don't see.
People are selling them and buying them and encouraged to put them up on
Sure.
their roads.
I don't see so much of a problem with that because it's something that will snowball over time. I think that the global interest in this thing happening will lead to the innovation of more technology, and eventually this newer and cleaner technology will eventually replace it. So I don't see it as that we're really shooting ourselves in the foot. I think that this is a step, though it's not perfect. It's a step toward the direction that we want to be going. Yeah.
Well, like now our thinking about the sustainability is really sort of converting whatever source of solar energy into the form of electricity and doing that. I just wonder whether in the physics world or whatever world there's any other way of thinking
Absolutely,
beyond
yeah.
electricity, and there's any way that's really clean and more direct to store whatever energy into the
Right. I partly just picked electricity because it's a convenient thing that we can all sort of, relate to. We've got the room lights and everything, right? And but really, you're right. That's not all there is, right? And so you could say like, oh well, why don't you just make cars into being electric cars, and then we'll just do away with all the other forms. It maybe not the most convenient thing. So as you were mentioning, that looking at some kind of biofuels, right? Looking at fuel cells, right? Ways to separate out hydrogen into oxygen and hydrogen, right? If I just said that right, to separate out water into hydrogen, oxygen, and then actually use that hydrogen, right? So there's some idea. Could you do that in a way that you have a car running off of hydrogen? Well, that's kind of cool. You're just basically combining it with the oxygen that's already in the air, and you're producing water, which is not no pollution, not toxic, right? So there are many ways to go about this. Also, what about just using sunlight to produce heat? That's where you need it, right? So those are also, there's a lot of different sort of angles that people are going at to try and figure out ways to harness this energy. Electricity is one of them. It's a big one, but it's only one of the many sort of strategies or approaches. And also the other big thing is that electricity can be conveniently stored. And believe it or not, we haven't really made a significant progress on battery technology. There's a lot of people who are doing research. For example, Steve Chu at Stanford is doing some really innovative work on lithium-ion batteries. But really, the cheapest battery out there still is a lead-acid battery. That's the cheapest one you can get. So in terms of the amount of energy that you can store and charge and discharge and the amount of times and stuff like that. So that's the reason why the Tesla Roadster costs so much, is because it's basically laptop batteries. It's lithium-ion batteries in there. So it's kind of interesting to imagine that we have still a long way to go in figuring out how to store this energy. That's another big aspect that's actually also hindering this thing. It's not just say that people want to stick with one thing that they know works, but it's also like, well, where are you going to store it, right? You might need it when you're not producing it. So. Any other questions? Maybe some student question? Yes.
So you mentioned wind energy as like one of the possible routes we could go.
Mm-hmm.
Are there any cons to wind energy?
Yes, and this may sound a little. So the question is so I mentioned wind energy as one of the possible solutions, and is there any sort of cons, or is there a drawback to doing this? And this may sound a little bit silly, but dead birds is actually an important con, and it may sound like, well, what is it, just a bird every once in a while? Actually, there's major migration patterns that for months and months you won't see any birds, and then suddenly there's lots of birds going through, and they're running into these windmills that are these wind turbines that are turning around at high velocities, right? So that's an issue, and I mean that's something that we need to consider also, with some sense of duty of, say, stewardship for our environment. Like, what are we, is this a good decision to make, or is there a way that we can mitigate that somehow, right? So perhaps studying migrational patterns and strategically placing the turbines in ways that don't make use of this. I'm not an expert in wind energy, so I do know that it involves moving parts, and moving parts often mean that they need to be replaced and maintained more. So that would be another disadvantage that I can think of. But at the moment, California has, I don't know exactly the number, but it's many gigawatts of wind power, especially down in Southern California. If you're ever driving, I think it's on when you go down the 5. You'll see a lot north of LA. You'll see a lot of these wind turbines as you're driving down. So that's providing electricity for the whole state. So yeah.
You mentioned, I think, in one of your earlier answers about other ways you can get energy from the sun, and I know there's some projects somewhere, maybe in California, that they have a bunch of mirrors, parabolic mirrors,
Yes.
focus, just use mirrors
Yes,
to
yes.
create a huge amount of heat on to
Totally.
the turbine or something.
Yeah, you can see this actually. I saw it from. I took a photo. I should have put this up on here. This is so neat. I took my last flight that I took. I was looking out the window and I saw this and I was like, whoa! And I was like telling my neighbor, like, hey, look at this. I don't think they understood how exciting it is. But basically, there's this. It looks like kind of like a spaceship kind of thing. The first efforts to do this were actually in Spain. The Spanish government's really interested in these kind of innovative ways of trying to think about ways to produce solar energy. So it's basically a bunch of mirrors that are on goniometers that track the sun, right? So they kind of move as the sun moves, and they're focusing the light all into the central tower. So you imagine this is the way that the ancient Greeks were burning down ships that would come onto shores by putting up these big mirrors and trying to focus the light, right? So we're now doing this it feels like science fiction. We're focusing that light onto a tower, and it heating up water makes steam, and then the story from there, right? The steam basically moves the turbine and you make electricity. So that's another possible way. And also, I was visiting in Hawaii on the Big Island a few years back, and I met this guy who was doing research similarly with mirrors. And the mirrors, instead of focusing way up into the air, focused onto these metal tubes that had mineral oil in them. And the mineral oil then circulates because of the heat differential and goes into a Stirling engine, which is, if you follow kind of the history of physics and in heat engines, this is like one of the very first types of heat engines that became popular. And this is actually used, just heat differentials actually makes this thing move up and down. And then again, you can use this. And he doesn't have very large space there, a couple acres, and it's producing 50 megawatts, which is enough to, definitely enough to power our campus. So thought that was really interesting.
And I guess my follow-up question is there some comparison of efficiency?
Oh, comparison of efficiency.
How does it compare to
Ooh,
solar? But if you don't know.
let's see. I would, I would venture. It's not the same as silicon, but it's just looking. It's an exploration to look for. I'd say that it's somewhere between the 10% is about what the number that I kind of remember from these things. So they're not, let's say, competitive, but they're thinking about this, right? And so the only way you can really learn is try it out and then think about, well, okay, what happened and how can we make that better, right? So maybe with iterating some more, you think, okay, well, this is probably a cheaper way to do it. Maybe it doesn't involve using silicon and all of its costly, energetic and toxic by processes. Maybe there's some other way. So it's part of an exploration, right? So it's kind of a learning adventure. So. Oh yeah, there was a question here, and then.
Yeah, so you mentioned that California State University East Bay was leading in sustainability. I was wondering if you knew any other CSUs that were making other unique changes or something that was specific or unique to that area.
That's a great question. So I know that Chico is working on that, and perhaps Jillian might mention.
Yeah. Solar array. I would also say Humboldt State has historically done a lot of really cool stuff with sustainability, been really student-led. Those are probably the big ones, I would say.
Great. Yeah, so if you're interested, especially...
I want to mention the fact that we, as well as Northridge and San Francisco, actually have hydrogen fuel cells on our campus.
Oh, right. I didn't mention that, yeah.
Unfortunately, they're using natural gas as their hydrogen feedstock.
That's right.
But that technology could be used with biogas, sewage gas, all sorts of sources of hydrogen. But we have one right behind the music video.
Right. So if you go walk over there, you can just go walk over there. There's this kind of sort of beige, white-looking building, and it's basically a pipe coming in of methane gas, and basically, sorry.
Yeah, natural gas.
Natural gas. So it's kind of a mixture, I guess, right? So basically, this is there's a chemical reaction that's happening that's producing electricity, but then one of the byproducts is it also produces heat, and that's being used also in principle to heat up the swimming pool and different buildings on campus. So no, it's not renewable because it's still not burning, but it's the chemical process of a fossil fuel. But at the same time, it's an exploration for a process that then could be used with other kinds of waste and other kinds of gases that may be more renewable somehow. So it's another interesting effort that we have on campus.
I know we have one
one question, but I do want to be respectful of people's time because we're over the hour. So just quickly to wrap up, and maybe we can talk after. Thank you for coming. The next speaker for the Affinity Hire Speaker Series is going to be during the Week of Inclusive Excellence. I'll leave this poster over at the table. It'll be Albert Gonzalez talking about, I love his title, Whiskey, Wood, and Worldview, an Archaeology of Industry and Rebellion in the Old West. It'll be in this room on Friday, 26th of February.
And,
thank you for coming. Thank you to our speaker.
Thank you for all your questions. I'll stick around here if you want to talk some more. Solar panels in our parking lots? Let's do it. Let's do it. And then people's cars are not hot either. Let's. I like it. I like it. Oh, thank you so much for coming, Carolyn. Oh, thank you so much.
I can tell you're a mighty fine teacher.
Oh, well, thank you.
You're welcome. That matters a lot. I've not met you. I'm Carolyn.
Hi, I teach in the building department.
Okay, very good.
This is Luis Villanueva.
Louis, it's a pleasure to meet you.